Imagine for a moment standing in a quiet room, holding a thin sheet of paper between your fingertips. Through that paper's surface, you sense a delicate boundary, something so fragile that even the slightest pressure might break it. Now think of that paper not as a physical object, but as an abstract threshold in the timeline of life, a silent divider that separates simple existence from a universe teeming with visible, communicative civilizations. This is a way to picture what some researchers call the Great Filter. The Great Filter is a concept that seeks to explain why, despite the vastness of the cosmos and the high probability of habitable planets, we do not see evidence of advanced extraterrestrial societies. It is connected to a much discussed problem known as the Fermi paradox, which asks us where all the aliens might be if life can arise so readily. The Great Filter proposes that at least one critical step on the path from simple chemistry to interstellar civilization is far less likely than we imagine, or else presents almost insurmountable barriers that very few, if any, species ever overcome. The idea was formalized in the late 1990s by an economist who was considering how to reconcile the apparent absence of visible alien civilizations. He suggested that somewhere in the sequence of events leading from lifeless matter to advanced life forms capable of traveling or communicating across the stars, there must be a stage so improbable that it filters out nearly all attempts before they can leave a detectable imprint. Identifying this stage would be challenging, as it might sit at any point in the long chain of biological and cultural milestones. First, life must emerge at all on Earth. Life arose from non-living chemical components over billions of years, a process known as abiogenesis. If the origin of life itself is an extraordinarily rare event, that might be where the Great Filter resides, right at the start, making simple life forms incredibly unusual. In that case, we exist because we somehow passed it, an event so special that it would explain the lack of other civilizations. Alternatively, life might be common, with microbes spreading easily. If that is so, then the filter could lie in another transition, such as evolving complex cells or multicellular organisms, or intelligence itself. Complex life took billions of years to appear on Earth. Multicellular organisms emerged after a series of major biological innovations. If it turned out that forming complex life is extremely unlikely due to specialized conditions, then perhaps countless planets hold nothing more than single-celled creatures. Another possible barrier could be the emergence of intelligence and technology. It took an immense span of time, multiple mass extinctions, and numerous environmental shifts for one species on Earth to develop tools, language, and eventually modern technology. If that step is staggeringly rare, that might be the Great Filter. Even if intelligence emerges, there remain other hurdles. Technological civilizations might be self-limiting. They could discover destructive technologies before attaining interstellar reach. Nuclear weapons, engineered pathogens, environmental breakdown from industrial activities, or runaway artificial intelligence could threaten a species long before it broadcasts a permanent presence into the galaxy. If such catastrophes are common, then the Great Filter could be a constant risk that most species do not survive, explaining why the universe seems quiet. Scientists have also considered the role of stellar and planetary conditions. Planets must remain habitable long enough for advanced life to evolve. Solar radiation, asteroid impacts, unstable climates, or harmful cosmic events might repeatedly reset progress. If advanced life's path is so fraught with setbacks that civilizations rarely make it far, it could be a northern face of the Great Filter. Some researchers have tried to estimate probabilities for each step. These calculations are uncertain and often rely on Earth's single example, which may not be representative. Earth's uniqueness could be a clue that we have already passed our Great Filter. Others wonder if the hardest step lies ahead, not behind. If so, then no matter how far we come, future challenges, perhaps related to sustainable resource use or preventing catastrophic misuse of emerging technologies, could stop us before we ever join a community of other spacefaring species. This line of thought is unsettling, but it remains a factual consideration under the theory's framework. All these scenarios connect to observed data. We see no clearly artificial signals from deep space and have found no direct evidence of alien visitors. The Great Filter helps organize these facts into a structure that highlights a single point of failure. It suggests that if intelligent, spacefaring civilizations were easy to achieve, then we would likely have encountered or detected them by now. Instead, we detect silence, and this silence can be explained if the cosmos is littered with evolutionary dead ends. Multiple fields of study have approached these ideas. Astrobiologists examine the chemical origins of life, searching for how easily primitive life might start under varying conditions. Geoscientists study Earth's history, pinpointing crucial evolutionary leaps and environmental changes. Planetary scientists look at places like Mars or Europa, wondering if microbial life ever flourished there. If we find independent examples of life in our own solar system, that might inform us about where the Great Filter could be. If life appears readily wherever conditions are right, then the filter probably sits much later in development. If we fail to find it anywhere else, maybe life's start is indeed the hardest step. No consensus exists on where the Great Filter lies. It is a hypothesis that fuels ongoing research and debate. Discoveries of exoplanets have shown that many stars host potentially habitable worlds. Upcoming telescopes and space missions will check these worlds' atmospheres for signs of life. If we discover signs of simple organisms elsewhere, that pushes the potential filter further down the line towards complexity, intelligence, or survival of advanced technology. Some simulations have tried to model the evolution of intelligent life under different assumptions. The results vary, but they often show how fragile and improbable long sequences of crucial steps can be. One small difference at any stage might mean no advanced life appears on a given world. The Great Filter hypothesis provides a structured way of looking at the silence beyond our planet's boundaries. It highlights that creating a galaxy-spanning civilization might not be straightforward. Understanding which step is so difficult remains an open question. As research progresses, we gain more data points, hoping to identify the factors that shape life's destiny. The known facts are that we exist, we look outward, and we have yet to find anyone else. The Great Filter reminds us that behind this scarcity could lie a series of improbable steps, any one of which might prevent the emergence or persistence of advanced extraterrestrial civilizations.